All right, this is chapter 2, descriptive statistics. You'll notice in your notes, there's a lot happening here at the start of this chapter that we don't cover. These are either things that you've seen in grade school or extensions of those. I do have a couple of definitions here. Um, Definition of a box plot, which you may need to come back to for a homework problem or two. These are just good ways to visualize data, but unfortunately, we don't spend a lot of time on that in this course. The other thing I want to point out to you is notice 2.3 measures of the location of data. We come back to that at the very end. The way this operates is I can kind of teach you A, then B, then C, or B, then C, then A, or C, then A, then B, but it's not like the alphabet in that there's always something that pins on something else. And so the book has decided to do it this way. I want to talk about it later, but it is called 2.3 in your book in case you want to reference it there, but I'm not going to talk about it to the end just because I think it explains easier. So we're going to jump into 2.5, which is measures of center of data. And we first start talking about not the center. We talk about everything else, that's outside of that. So an outlier is a data value that is not consistent with the bulk of the data. So that's literally the opposite of a measure of center. It's a single data point, but it's not anywhere near the middle. It's not anywhere near where the rest of the data is. How do you define an outlier? There are different methodologies to do that. However, we're going to, for the most part, just skip over that here. If you use Excel or a different software package, it'll kind of automatically calculate it for you. Um, it's not really a big part of this class. What's important is that you understand outliers and what they can do to the data set, but less so trying to pick it out yourself. Just understand, hey, this isn't consistent and it's going to cause some potential problems. And so, what are these complications? Well, we're going to talk about that here on the rest of this page. The idea is that there's really three possible options when you have outliers. The first is that the outlier could be a legitimate value that just represents natural variability and needs to remain in the data set. The idea with this is if I were to ask you and your classmates to all go flip a coin 100 times tonight and report back to me via email the results of those coin flips, tell me how many heads you got. If somebody replied back to me that they had 71 heads, that would be an outlier. It would be not consistent because most of you are probably going to get maybe 45 to 55. If somebody replied back 71, I would say that's an outlier. What does that mean? Well, it could be a legitimate value. It could just be sometimes weird things happen. You think about sports. Sometimes teams shockingly lose way more games than you think, or they win way more games than you think, even if it's a good team, right? Or you think about, um, anything in life. Some people are really short, or really tall, or really fast, or whatever it may be. Sometimes they're still normal humans. It's just that there's natural variability with regards to people's heights and people's speed and all sorts of things. And that sometimes that variability just exists and it just happens and it is what it is. No big deal. Don't actually do anything. A second option is that there's a mistake that was made and we need to correct that or remove it. There's another scenario. You email me back 71 heads and I reply back to you and I say, are you sure this seems a bit high? And you say, oh my gosh, a number pad, the 7 is right above the 4. I meant to say 41. And I'd say, oh, 41, is a whole lot closer. It's only 9 away from what we would have expected, not 21 away. And that was just a mistake. And so then I can go ahead and manually in my database correct that 71 to 41. The issue, and we haven't even got to the third one yet, but let's just talk about the first two. The issue is, how are you going to know which one's which, right? In this case, I could ask you, but in a lot of cases, we can't go back and ask the people who we collected data from. So it's hard to know between the two which one it is. And if I can't ask, then I can't correct. I could just remove. So I could then now I have to make a decision. Do I think it's an error and I just want to remove it, or do I want to say it's just natural variability and leave it in, right? And it's kind of I don't really know how to handle it. I think we haven't even got to the third one yet. That last option is that the observation belongs to a different group than those measured. It's not actually the same. This goes back to that representative sample that we talked about previously. It's actually just not part of the same group. It's its own special entity. And so hypothetically, you email me 71 heads and I reply back and I say 71, that seems a bit odd. And you say, well, Funny story, I used the only coin I could find and it was bent funny, and that might have affected how the coin landed, and so that might be why. Okay, now I would say now the bent coin is a different group than a normal coin. Now then I have to decide, do I want to remove it because it's a different group, or do I want to say, yeah, but bent coins could still fall back, it's still 50-50, right? And again, hypothetically, what if I can't ask you about your data? Then now I don't even know if that's one of the possible options. So the issue that we have here with outliers is we don't necessarily easily know which of these options an outlier could come from. Okay, and in your notes you see there, we say that only remove outliers with proper justification. Now, I'm not going to ask you to remove or not. That's just a general, tip. What I want to paint the picture of is less about what to do with outliers, because I'm not going to ask you to do anything with them. What I want to paint the picture for you on is that outliers are concerning because you don't know how to handle them easily, and we'd like to not deal with outliers. Okay, that's the main takeaway from all this. Is I've set all this up to tell you we'd like to not deal with outliers. Okay, how do we get around that? Well, if we deal with statistics that are robust or resistant, those are synonymous terms, different textbooks use different things, robust or resistant, then the presence of outliers doesn't cause it to change very much. And you might hear this and say, wait a minute, this feels like it came out of left field. We were talking about a data set. We were talking about measures of center. We were saying, okay, outliers are not anywhere near the center. Now all of a sudden you're talking about a statistic. Remember, a statistic is a numerical measurement that comes from a sample. Well, remember, we're trying to build a bunch of pillars to put everything together later and start building up a house, a structure. And a statistic is a thing that we are going to consistently use later in the course to make an inference on a parameter. Remember the whole purpose of the course. So what we're talking about now is if I'm able to use statistics that have this property of robustness or resistance, then I don't have to care about outliers. So right now where your brain should be is, okay, we know that later on we're going to be using statistics to make inferences on parameters. We know also outliers are going to cause problems in my life. So if I use specific statistics that are robust or resistant, then I don't have to worry about outliers. If I don't use statistics that are robust or resistant, then I do have to worry about outliers. Okay, so that's where we're at going forward. Now, as we move forward, let's actually talk about measures of center. The first measure of center we're going to talk about is the mean, which is something that you should be very familiar with. It's the average of a data set. Those two terms are synonymous. As we said before, we should never just say, a mean or a percentage or something like that. We can always come back and define where did it come from, whether it's the sample mean or the population mean. So I'm going to differentiate here between the two. A sample mean is the mathematical average of a data set. Its definition is listed below. Now, these may be some new symbols for you, maybe not. X bar is the symbol that we're going to use when defining the sample mean. This is our first of many symbols that we're going to have. So anytime you see X bar, you think sample mean. Anytime you think sample mean, you think X bar. What this means is this capital Greek letter sigma is summation. So we're going to sum up all the individual x's and divide by n. You know how to find an average, right? Add up all the values, divide by n. That's all this is saying right here. We're going to add up all the x's and divide by n, and that gives me my sample mean. Lowercase n is the second symbol now that we have. That is the sample size. And we're going to contrast this with the population mean, which is, of course, the mathematical average of a population. And it has a symbol using the Greek letter mu. And that's how we define it right there as the sum of all the x values. But now we're going to divide by capital N, which is the population size. As we move forward, we're going to have a lot of symbols that we're going to need to learn. Take note that our population values are going to often, not always, there's one exception we'll talk about later, but often be Greek letters. Our sample values often will be English letters. And so that's one easy way to differentiate, are you working with a statistic or a parameter? Some properties of means in general, whether it's population or sample, is that a mean is likely not a value in the data set. Now, that doesn't really matter. It's simply something I'm telling you so that you don't freak out if you get a value for the mean that's not in the data set. And you might be like, well, yeah, duh. But I'm surprised that sometimes when students, when I'll ask a question about what the mean of something is, and they'll say, they'll give a value, we'll say, what's the mean of people's shoe size? And we can work the problem and it'll say 8.75. And people will be like, wait, but you can't have an 8.75. Okay, that's how means work. They aren't always values in the data set. They often aren't. What's the average family size, right? The average family is 2.3 kids. You can't have 2.3 kids. That's the way means work. They don't have to be values. The data set, no big deal. The second property is that it is not robust or resistant. So going back to what we just talked about, that means if we're dealing with means, we have to be a little bit concerned about the presence of outliers because it could cause problems and it could lead us into that. I don't really know how to handle this situation, which we said we wanted to avoid. We'd like to use statistics that are robust or resistant. The next property is that it is the most commonly used metric for quantitative data. Remember, quantitative data is data that we can do our normal math with. And this is where you should say, okay, that's a little bit weird. We said we wanted to use robust or resistant statistics because that means we don't have to worry about outliers. And then in the next breath, you say, but it's the most commonly used metric. Put a pin in that thought. We will come back to that shortly. And then the last property is that it cannot be used with qualitative data. Remember, qualitative data, things like zip codes or phone numbers, things like that, which that makes sense. We already talked about that when we discussed that type of data. You could not average people's phone numbers. The number you dial would not be the location between the two people. It would just be a random number that's somebody completely different. So a quick example, you should be very comfortable with finding means, but let's just work through this real quick. You will be asked to do this a little bit. On homework, you have one exam question about this. The data set will be small and simple. Here are home run totals. There are 5 of them. It says find the mean using the appropriate symbol. Notice I'm asking for you to use a symbol. And at this point, you should be thinking, okay, it's either X bar or mu. And if you want to go ahead and pause, work through this problem, think about the symbol, now would be a good time to do so. I was not asked to find the sample mean or the population mean. So that would be one giveaway, right? If I said find the sample mean, you'd say, oh, X bar. If I said find the population mean, you'd say, oh, it's mu. So you don't have that giveaway. However, we see that the following home run totals, a sample of 5 players, right? There are more than 5 players who meet these criteria. This is just a subset of them that makes this a sample mean. So we're going to use the symbol X bar. We add up all 5 of those numbers. We get 95 as the numerator. There are 5 of them, so we divide by 5, and that means that X bar is 19.